The fundamental theorem of calculus. In this section, you are going to learn very powerful tool to evaluate definite integral called fundamental theorem of calculus. You could use FTC as an abbreviation for fundamental theorem of calculus. Given small f of x is continuous on closed interval a to b, and small f of x is equal to the derivative respect to x of capital F of x, which means then capital F of x is the antiderivative of small f of x, then integral a to b of f of x dx is equal to capital F of x evaluated from a to b, which is equal to capital F evaluated at b minus capital F evaluated at a. To understand this a little bit better, let's take a look at integral a to b of small f of x dx. And we just said capital F of x is the antiderivative of small f of x. So when you integrate small f of x, we will get antiderivative, which is capital F of x plus some constant c. And when you evaluate that from a to b, you would plug b for every x you see. So you will get capital F of b plus c. And then you're going to have to subtract capital F of a plus c. And as you distribute the negative, c is going to be canceled, and you will only get capital F of b minus capital F of a. And this is what it's saying. So it is a lot simpler than what we had to do in last section to evaluate definite integral. So let's do a few examples to feel how powerful this tool is. So what would be integral of 1 to 5 of x dx? What we did earlier was we would draw the graph, and then we would look at the graph from 1 to 5. We will partition that and use the limit and the sum of infinitely many rectangle to find this definite integral of this. Or we would draw the picture and geometric formula to evaluate this integral. But now, knowing antiderivative of x, which is 1/2 x squared, and we would like to evaluate that from 1 to 5, and by FTC, this is equal to 1/2 x squared evaluated at 5, which is 5 squared, subtract 1/2 x squared evaluated at x equal 1. So then that would be equal to 25 over 2 subtract 1/2, which is equal to 24 over 2, which is equal to 12. So we found the answer very quick. Let's look at another example. What is integral of 0 to pi over 3 of secant x tangent x dx? What is the antiderivative of secant x tangent x? Correct. It would be secant x. So this is secant x evaluated from 0 to pi over 3. And now that would be equal to secant x evaluated at pi over 3 subtract secant x evaluated at x equals 0. And secant of pi over 3 is 1 over cosine of pi over 3 minus 1 over cosine of 0. And cosine of pi over 3 is 1/2. So I have 1 over 1/2 minus 1 over cosine of 0 is 1. So you have 2 subtract 1, which is 1. So you found the answer. How about integral 0 to 4 of absolute value of x minus 1 dx? Well, absolute value of x minus 1 is a piecewise defined function. So let's rewrite this as absolute value of x minus 1 is equal to x minus 1 if input is positive, and input is positive if x is greater than equal to 1. And it will be opposite of x minus 1 if x is less than 1. So now we can split this integral. This is integral 0 to 1. Since 0 to 1 is less than 1, you would need opposite of x minus 1. When you distribute the negative, it is minus x plus 1 dx plus integral 1 to 4 of 1 to 4. Absolute value of x minus 1 is x minus 1 dx. And now find the antiderivative of negative x plus 1, which is negative 1/2 x squared plus x, evaluate from 0 to 1, plus antiderivative of x minus 1 is 1/2 x squared minus x, evaluate from 1 to 4. Now, you are going to evaluate negative 1/2 x squared plus x at 1, and then you're going to subtract. Because you're going to subtract, make sure you put parentheses. Negative 1/2 x squared plus x evaluated at 0. And then now you're gonna add with 1/2 x squared minus x evaluated at 4. Subtract 1/2 x squared minus x evaluated at 1. So then negative 1/2 plus 1. This is a 0. And then this is a plus 1/2 times 4 squared is 16. Half of 16 is 8. Minus 4 minus 1/2 minus 1 is plus 1. So then negative half minus half is negative 1 plus 1 is 0. 8 subtract 4 is 4. 4 plus 1 is 5. So the answer is 5. Now, recall position function that we learned in the past. We have learned that when you take the derivative of a position function, you get velocity function. And when you take the derivative of a velocity function, you get acceleration function. So that was the derivative relationship. Therefore, integral relationship would be you could recover velocity function when you integrate acceleration function, and when you integrate velocity function, you could recover the position function s of t. Now, displacement from starting position over the interval a to b can be found by taking integral of velocity function a to b dt. And what this is saying, let's say you start from the origin 0. Let's just say you're starting from origin. You went 1 unit to the left, and then you came back 1 unit to the right, and it took 1 second each over the 2-second interval. Then your displacement now is 0 because you started at origin. You went 1 unit to the left, 1 unit to the right. Now, total distance traveled during the interval a to b is equal to integral of absolute value of your velocity function from a to b dt. And the example I just mentioned, that would be 2 units because you're going to take the absolute value. So moving left would still count as positive unit. And you will have a positive 1 unit plus positive 1 unit. So you would have traveled 2 units total. Let's do an example here. Suppose that the velocity of an object is given by the graph below. The areas of the given regions are 20 above x-axis, 9 below x-axis, and 7 above x-axis. Name the intervals where the object is moving to the right. Object is moving to the right when velocity is positive. You can see at t equal 1, v sub t is positive, and at t equal 5, v sub 5 is 0. So that doesn't count since it is 0. So that's when t belongs to 1 second to 5 second, but 5 is not included. Union. Now v sub 8 is 0, but as soon as t is bigger than 8, it is a positive. So it is 8 to 10. And 10 is included because you can see v sub 10 is right here, which is a positive value. Name the intervals where the object is moving to the left. Object is moving to the left when velocity function is negative because it's to the left. And that will be right there. So object is moving to the left when t belongs to interval 5 to 8. Find the displacement of the object over the interval 1 to 10. As you see above, displacement over the interval 1 to 10 is just the integral 1 to 10 of v sub t dt. And they gave you already area under the curves. So 20 is a positive value since it is above x-axis. And then 9 is negative because it's below x-axis. And 7 is positive because it's above x-axis. Therefore, displacement over the interval 1 to 10 would give you 18. Find the total distance traveled by the object on the interval 1 to 10. Total distance during the interval 1 to 10 is integral 1 to 10 of absolute value of v sub t dt. What is the absolute value of v sub t? If you look at this graph, when you take the absolute value of positive, it stays the same. And then when you take the absolute value of negative value, it becomes a positive. And absolute value of positive is a positive. So graph's gonna look like that, and this was a 20. Now negative 9 is gonna be positive 9. Positive 7 stays positive 7. Therefore, total distance traveled by the object on the interval 1 to 10 would be 20 plus 9 plus 7, which is equal to 36. Let's do another example. A particle travels with a sub t, acceleration function, is equal to sine t, and v sub 0, velocity function at time 0, is negative 1. Find the velocity equation. We just learned that velocity function can be found by taking integral of acceleration function. So let's go ahead and find velocity function v sub t is equal to integral of a sub t dt. And our acceleration function right now is sine t dt. And integral of sine t is, yes, negative cosine t plus the constant of integration c. Now, how am I going to find the c? From the initial value of a velocity, the fact that v sub 0 equal -1. So v sub 0 is equal to negative cosine of 0 plus c. And it says that value is equal to -1. And what's the cosine of 0? Yes, cosine of 0 is 1. And what's negative cosine of 0? Well, cosine of 0 is 1. So negative cosine of 0 is -1 plus c equal -1. So you add 1 both sides. You know that c has to be then equal to 0. And therefore, the v sub t you're looking for, velocity function, is equal to just negative cosine of t, since c is equal to 0. Find the displacement of the particle over time period 0 to pi. To find the displacement, you need to take integral from a to b v sub t dt. And your a is 0 and b is pi. So let's go ahead and evaluate. 0 to pi, v sub t is negative cosine t dt. And since -1 is constant multiple, we could pull that out, which is equal to negative 0 to pi cosine of t dt, and integral of cosine is sine. So I get negative sine t going from 0 to pi, and that would be negative sine of pi minus the sine of 0. But what is the sine pi? 0. What's the sine of 0? 0. So this will be negative 0 minus 0, which is equal to 0. Find the total distance traveled by the particle on 0 to pi. So now, the total distance could be found by taking integral a to b of absolute value of v sub t dt. And it is 0 to pi absolute value of negative cosine t dt. Now, absolute value of negative cosine t is the same as 0 to pi absolute value of cosine t dt. So let's recall what is the cosine graph looks like. Cosine function start at 1, go to 0 at pi over 2, and it's a -1 at pi, and then back to 0 at 3 pi over 2, and back to 1 at 2 pi. This is what cosine graph looks like, and you will like to just take the absolute value of cosine t from 0 to pi. And because 0 to pi over 2 is already positive, this is fine. But from pi over 2 to pi, it is negative. So when you take the absolute value, it's gonna come back up here. So what we need to do is rewrite the absolute value of cosine t. We know absolute value of cosine t is cosine t from where? When t is from 0 to pi over 2. And then it is, we gotta take the opposite of cosine t to make it positive, since the pi over 2 to pi, cosine function is negative. So t from pi over 2 to pi, it is opposite of cosine t. So we are gonna have to split this to integrate from 0 to pi over 2. It is cosine t, since in that time interval, cosine function is positive. and from pi over 2 to pi, because cosine function is negative there, and it is negative cosine t dt. So then this is going to be equal to, what's integral of cosine t? It's sine t, going at 0 to pi over 2, plus, it's a plus, but we can pull out the negative since it's a constant multiple. So it's a negative. And integral of cosine t again is sine t from pi over 2 to pi, which is equal to, then first part of evaluation give me sine of pi over 2 minus sine 0 minus sine pi minus the sine pi over 2, which is equal to, there you go. So what is the sine pi over 2? Sine pi over 2 is 1 minus sine of 0 is 0 minus sine pi is 0 again, and sine pi over 2 is 1. So finally, you get 1 minus negative 1, which is equal to 2. So do you see the difference? After pi units of time, the particle is in the location 0. However, total distance traveled during the pi units of time is 2 units. That's what this is saying. Mean value theorem for integrals. Wait a minute, didn't we learn this before? Yeah, that was a mean value theorem for derivatives. And this is now mean value theorem for integrals. So let f be continuous on the interval a to b. Then there exists c inside of that interval a to b such that integral of a to b of fx dx is equal to quantity b minus a times f of c. Man, what is it saying? Let's look at the picture under there. We're assuming this is function f of x. And now what would it mean then, the integral of a to b of f of x? Well, because right now my function is positive, integral of a to b would mean the area under this curve, right? And they're saying integral a to b of f of x dx, which is the area under this curve on a to b, is equal to, they said, b minus a. Okay, this is b and this is a. So when you do b minus a, I get this. Is that right? So b minus a is this. This is b minus a. Times c, they said, is in that interval. So for certain c, let's say that c is here. Then what's f of c? F of c will be the height of this function since you plug the c inside of your f. So then this is f of c. So if you multiply b minus a times f of c, that's the area of a rectangle from a to b. So that length is b minus a and height is f of c. And that's the area of a rectangle. So I have this. But look at what the mean value theorem for integral is saying, that these two are equal. So what it's saying is, if f is continuous function on a closed interval a to b, then there exists a c that would give you the height of a rectangle such that area under the curve of a to b is exactly equal to the area of a rectangle whose base is b minus a and whose height is f of c. And they're saying such a c exists, is what this theorem is saying. All right, I hope you understood. So let's go ahead and do an example of this problem. F of x equal 4x squared on the interval 0 to 3. Find the value of c guaranteed by mean value theorem for integrals. Okay, so fx equal 4x squared is a continuous function on a closed interval 0 to 3 because this is a polynomial. It's a parabola precisely, and it is continuous on all real numbers. So it is continuous on closed interval 0 to 3. I should mention that first because otherwise I cannot use mean value theorem. So I will say f is continuous on R, all real numbers. So it is continuous on closed interval 0 to 3. Thus, mean value theorem for integral applies. Therefore, you are convinced that such a C exists that is mentioned in mean value theorem. And what the mean value theorem says was integral of closed interval a to b of f of x dx is equal to the length of rectangle b minus a times the height f of c for some c inside of interval a to b. And here a to b is 0 to 3. So let's apply. That's the integral 0 to 3. My function is 4x squared dx is equal to 3 minus 0 times f of c. My goal is to find such a c, and I don't know what the c is yet. I see that everything's gonna become a number, and f of c will have a expression with the c in it. So I will have only one variable c, and therefore I will be able to solve it. So here we go. What's integral of 4x squared? 4 is a constant multiple, and integral of x squared is 1 over 3 x to the third power from 0 to 3. 3 minus 0 is 3. F of c, since f of x is 4x squared, f of c is 4c squared. All right, then I have 4 third x cubed from 0 to 3 equal 12c squared. And when you evaluate this, I get 4 third 3 cubed minus 0 cubed equal 12c squared. And 3 cubed is 27. So 4 third times 27 equal 12c squared. Let's cancel the 3 and 9. So I get 4 times 9, 36 equal 12c squared. Divide both sides by 12. I get c squared equal 3. So by square root property, c is plus minus square root of 3. But remember, mean value theorem says such a c has to be in the interval 0 to 3, a to b. So I need to pick a c that applies in the mean value theorem. So negative radical 3 is not the one. Thus, c must be equal to positive radical 3. 4. Average value of a function on an interval. This is not new. It is still tied from mean value theorem for integrals. So here is what's the average value of a function. For a rectangle, we had an area of a rectangle was equal to base times the height. So then area over base would give you the height of the rectangle, right? So now that height is what is the average value of a function on a to b. So here we go. Just a little ago, we learned that integral a to b of f of x dx, which is the area under the curve of f of x from a to b, was equal to an area of a rectangle whose base is b minus a, and for some c in that interval a to b, such that f of c was the height of a rectangle. We were saying that if you have a continuous function, such a height exists, right? And that f of c is called average value of a function on a to b. To find that average value of a function, all you have to do is divide both sides of this equation by b minus a to get f of c equal area under the curve divided by b minus a, and that is called average value of a function f on a to b. So here is the definition of average value. Let f be integrable on the interval a to b. Then the average value of f on the interval is given by average value of f on a to b is equal to 1 over b minus a of integral a to b of f of x dx. I would like to keep that equal to f of c that we learned from mean value theorem for integrals. Example. Find the average value of f of x equal 3x squared plus 6x plus 5 on the interval 1 to 4. All right. So what is average value? That was height f of c, which was equal to 1 over b minus a integral a to b f of x dx. So then let's apply. My a is 1, b is 4, and here is my f of x. So that is going to be equal to 1 over 4 minus 1 integral 1 to 4 3x squared plus 6x plus 5 dx, which is equal to 1/3. And can we integrate it? When we integrate 3x squared, it's a 3 over 3 x to the third plus 6 over 2 x squared plus 5x from 1 to 4. Let's clean it up. So I have a 1/3 times 3 over 3 is 1, so I have a x cubed plus 6 over 2 is 3x squared plus 5x from 1 to 4. And when you evaluate this, I have 1/3, and the upper limit, I get 4 cubed plus 3 times 4 square plus 5 times 4. Subtract lower limit, 1 cubed plus 3 times 1 square plus 5 times 1. That is equal to 1/3. And when you calculate 4 cubed plus 3 times 4 square plus 5 times 4, you get 132. Subtract 1 plus 3 plus 5 is 9. So then that is 1/3 times 123, and it is equal to 41. So we found the average value. Next, second fundamental theorem of calculus. So let's see what the second fundamental theorem of calculus has to say. Given fx is continuous on an open interval containing a, then if you take the integral of your function from a constant to a variable x, you are going to get a function there. And then if you take the derivative again, you just get what original function was with variable x in it. All right. And also using chain rule. When you take the integral of f of t from a constant to a function and then take the derivative again, then all you get is f of g of x, But because it's a derivative and your g of x is like u, you need to multiply by u prime, which is g prime of x, just like a chain rule. So let me show the fourth one. Okay, so derivative of integral of a to x of f of t dt is f of x. Why is that? So let's say antiderivative of little f of t is capital F of t. So I will have d dx of, once I take the integral of little f of t dt, I will get antiderivative capital F of t going from a constant a to x, right? But then d dx of, I haven't taken derivative yet, but when you evaluate this integral using fundamental theorem of calculus, I have to put the upper limit, subtract the lower limit. So when I plug it in, I'm going to get capital F of x minus capital F of a. This is a function, and this is just a number since a is a constant and x is a variable. So now when you take the derivative of each, you're going to get little f of x. And derivative of a constant is 0. So I get my f of x back. So when you have integral of a constant to variable x of f t dt and take the derivative back with respect to x, all you get is the same copy of what's inside as outside with the variable switch it to x. That's what it's saying. And then I will also show you why this is the case using proof. Same as what we just did. So let's say little f of x is the derivative of capital F of x. When you take the integral of little f t dt from a to function g of x, then I still have a d of x. But when you take integral, I'm going to get capital F of x antiderivative from constant a to function g of x. So when you evaluate that integral, I get d dx of f of my upper limit is g of x minus capital F of a constant. But when you plug a number into your function, it's just a number. So this is just the number. And f of g of x is now composite function. So when you take the derivative of a composite function, you gotta use chain rule. So when you take the derivative of that by chain rule, I get little f of g of x times derivative of inner function. And then derivative of constant is 0. So all you get is f of g of x times g prime of x, which is the result of this. Okay, so let's do an example. What is the derivative of integral of 5 to x squared of 1 over 3t plus 1 dt? So your upper limit is not just x. It is x squared. It's a function. So that's your g of x. So according to the second fundamental theorem of calculus, what I have to do is I have to plug x squared in there where the t is. But because your upper limit is not x, it's a function, you gotta multiply by g prime. So this is your g of x. So when you integrate and take the derivative back, I should get f of g of x times g prime of x is what I have to get. So now first of all, where the t is in your little ft, you have to just plug g of x in there. So then you're gonna get 1 over 3x squared plus 1, and then I gotta multiply by g prime, and my g of x is x squared. So what's my g prime? 2x. You got it. So therefore, the final answer is 2x over 3x squared plus 1. Good job. Let's do one more. Before I do the last problem, I want you to think about what would I do if I have derivative of integral h of x to g of x of ft dt. What would we do? As we have seen from previous proofs, let's do it. Let's literally use fundamental theorem of calculus to see what the result has to be. So let's say antiderivative of little f of t is capital F of t. Then when you take the integral, I would get capital F of t from hx to g of x is what I get. So when you evaluate, I should get capital F of upper limit g of x minus capital F of lower limit h of x. Now, when you take the derivative of each, you can see that I needed to use the chain rule to both the function. So first one, my result will be little f of g of x times chain rule g prime of x minus small f of h of x times chain rule h prime of x. Okay, I think this will be also handy to have that as a third formula of second fundamental theorem of calculus, since I've seen a lot of problem like that. So let's use that, although our bottom limit is not really h of x, as it's just an x. So then you're just gonna get little f of x. So let's do the second problem. So what's the derivative of integral of x to 4x cosine of radical t dt? So this is your g of x, but this is just an x. So what I'm gonna get is cosine radical of g of x, and my g of x is 4x, times g prime. And because gx is 4x, g prime is 4 minus, and then I'm gonna get f of x. Because my lower limit is just x, it is not a function, it's just an x. So you're just gonna get regular little f of x, which is cosine radical x. So just write it better. My answer should be 4 cosine radical 4x minus cosine of radical x. And that's gonna be the answer for this problem. All right, guys, good job, and I'll see you in next section.